Hello, Ashima.
Ma'am, good evening. Welcome.
Yeah, hello, how are you?
We are fine, ma'am.
Okay. I've started my video for briefly. I don't know whether you can see.
Yes, ma'am. We can see you and we can hear you completely fine.
Okay. So, can I keep my video switched off?
Yes, ma'am. Yes, ma'am. Yes, ma'am.
Okay.
We have 2 or 3 minutes before we'll begin at 7, if that is okay.
Let me also
I can stop sharing. Yes, ma'am. You can stop.
Hello. Hello.
Yes, ma'am. Yes, ma'am. It is visible and moving also. Thank you.
to see. Going, right?
Yes, ma'am. Yes, ma'am. All is okay.
Okay, any pointers now? Because so this is how I have organized my talk. I'm going to present little bit of work that we have done in our lab. And I would say whenever you find that this much is enough, so whenever you say this much is enough, I can stop and then start taking questions.
Sure, ma'am. Sure.
There are some questions in chat also.
No, not yet. But we've just started the recording, ma'am. We'll wait for around 3-4 minutes more and then we'll begin.
Yeah.
Right, so just 7 p.m. sharp. I think we have a few attendees who have already joined. So Dr. Anubha ma'am, if you can permit, we will want to announce a short pretest before we can begin with the proceedings of today's webinar.
Sure.
Yes. So I will request my team, Sonu, to please share the link of the pretest. So all of those who have joined are requested to kindly complete the pretest. The link is in the chat box for everybody to see. If there's any problem, then please let us know. For attendees who have joined us just shortly, we can share the link of the pretest again. So all attendees who have joined can quickly fill up the pretest. So I'll request Sonu to reshare the message if needed. Right. So as the attendees are about to finish the pretest, with permission from my group, if we can begin today's webinar. So it is my honor to welcome Dr. Anubha Gupta ma'am. Ma'am is a BTech and MTech from Delhi University in Electronics and Communication Engineering. She did her PhD from IIT Delhi in Electronic Engineering, followed by Masters from University of Maryland, USA. And she served in different professional capacities, right from Assistant Director in the Ministry of Information and Broadcasting, Government of India, to being a faculty at NSUT Delhi and IIIT Hyderabad. Currently, ma'am serves as the professor at IIIT Delhi She's also the in charge of the signal processing and biomedical imaging lab at a Center of Excellence at IIIT Delhi. She has two US patents and two Indian patents to her name, and she has been awarded numerous awards, a few of them being SERB Power Fellowship 2021, IETE Professor SVC IR Memorial Award 2022, and Lab to Market Challenge by the India AI Group, which her team won in 2023. So we are indeed honored to have you with us for this webinar series of the MAMC MIC group. And I think we can begin today's session. Over to you.
Thank you so much. Thank you, Ashima, for giving me this opportunity to speak. And I am also thankful to all the participants who have taken time to attend this webinar. So I would be presenting briefly about some of the application areas and some of the problems that we have worked on. But in the end, I would like to take questions. If there are lots of questions, I would be very happy, because based on my experience on working on different healthcare data, we have sort of understood a lot of nuances that go in the domain. So my lab, as Dr. Ashima also mentioned, it is SBI Lab, Signal Processing and Biomedical Imaging Lab. We have worked extensively on cardiovascular disorders. Then in digital pathology also, we have worked on cancer imaging, particularly blood cancer imaging. Then we have also worked on cancer genomics, whole exome sequencing data analysis, RNA sequencing data analysis, microarray data, etc. We have built some for multiple myeloma risk predictor models, which we say cancer survival analysis. We have also system, smaller GPU systems, and in neuroscience, etc. I'll be largely presenting the work from the first 3-4 threads here in brief, so as to give you a glimpse of what all we have been doing. So what are the challenges with current technologies? If we say that the way we say that these are the gold standards with which we work, for example, in pathology, we'll say that the gold standard is that you look at an image under the microscope and you count the number of cells for certain disorders or look at the morphological changes. And then the reports prepared by pathologists are considered to be the gold standards. But are these solutions scalable? So there is a problem. For example, in COVID-19, we saw that the number of blood test requirements were huge, but the number of people who could serve in those labs were relatively less, because even pathologists and doctors were also falling sick. Similarly, are these technologies always affordable? So if we are working at digitization of the technologies, then that means that per sample cost can reduce considerably, and that brings it to the technology to affordability. Not only that, for example, there are many tests where maybe the test requires, say, biopsy, and so that means that you have to, or maybe, for example, angiogram, etc. when you take. So some are invasive technologies that make it a bit costly, but if somehow we can solve those problems using AI, then that can become affordable. Accessibility is another bigger problem, because the current technology requires that you would be going to a hospital, getting that test done, and there only the analysis would be done. Whereas if the technology is digitized, so that means that maybe a small device can be deployed in a rural area where the data is collected and it is uploaded on the cloud, and then the analysis happens and the reports are moving out. So the challenge is, overall, we say that it leads to poor health index outcome. But if it is digitized, the scalability makes it also affordable, because it leads to reduced cost per additional sample. Moreover, during the cases of pandemics, so that means that you can handle a large amount of load in a smaller amount of time. Turnaround also increases because now with the movement in the technology, with the hardware development as well as the software development, there are very efficient systems that can actually do huge amount of computations within no time. So it also reduces the turnaround time, not only in terms of the compute, but also in terms of giving the inference out. Because now the pathologist need not be there in the lab and doing all the analysis, but maybe some machine is doing and generating the report. Pathologist can be anywhere, maybe sitting in his office or at his home, and then sees the report and then do the re-annotations or little bit of tweaking on the report as he requires, and then can sign off. So it also eventually it reduces the turnaround time. Increased accessibility in rural and urban areas, supports personalized treatment plans and research, etc. Enhances early disease detection because the moment you have huge compute and the models are scalable, the tests are, you can do massive testing. So that means that you can also now do mass screening of population, and so early disease detection can also happen. And of course, ease of deployment is there. So one example is, for example, in pathology, the earlier or the gold standards are you are making a slide and watching it under the microscope and then signing off the report. But now currently we are also looking at whole slide scanner or automated microscopes. So motorized automated microscope where there is a stronger software. So it actually scans the whole slide, then annotates the cells, the segmentation, classification, everything happens. And now it can be displayed on the screen and the pathologist can actually look at that. If there is any error, can fix that error and then sign off the report. So it is much easier compared to the earlier one. So now let me present you some of the work that we have done in cardiovascular disease diagnosis. I am presenting only a few work under every thread, but let's see whether you see the merit in that. So this is one of the works that we did on explainable AI decision model for ECG data for cardiac disorders. And this solution, although proposed in 2022, was still a very relevant until maybe last year. I can say that it was still one of the state-of-the-art methods, and it also won India AI's Lab to Market Challenge. So what was the problem? That we said that, for example, if you look at the scenario in a hospital, say in an ICU, we see that we do 24 hours monitoring of ECG data. Similarly, in ambulances, you have ECG monitors which are there. Now, if you also look at, say, consider a scenario, say during the night time when a patient walks in and someone has to maybe complaining of some heart pain, etc., and ECG is done, a specialist or a cardiologist may not be available at that time. Now, same thing may happen in ICU all the time, the cardiologist is not there. So what do we want? We want that if we capture the ECG data, for example, which is a 12-channel data, can we build an AI model that can do disease labeling on that data? So we built a model, an AI model, and most of the time whenever you build a model, the bigger critique is that how does a cardiologist trust that whatever model you're built is really good or not? So how do we know that it's really going to work and it's not doing some random stuff and just doing some classification? So here we built our custom in-house architecture, which was based on convolutional neural network, is very popular, where you can build your own, you can add your own layers. So we added our own, built every layer of that architecture in a custom design manner, did lots of iterations, and finally achieved one model that we tested. Now, once we built this model, it was basically on 5 superclasses. The classes were whether it is a conduction disturbance, myocardial infarction, or SCTC change or hypertrophy, or was it a healthy one? Now, once we built that classifier, so it was a 5-class classification, then we wanted to test whether the model is really seeing what a cardiologist would have seen in the ECG wave, and then would have said that yes, it belongs to this class. So you see one example, say this patient was suffering from right bundle branch block, which is a subclass of under conduction disturbance. So here, this is a normal lead 1 ECG. This is how it would look like. Now, if the person is suffering with this, sometimes in lead 1, we see a slurred S wave pattern. So this is how the S wave gets slurred. So this reference style has been taken from the net. Now, this was the data of the subject. Now, once our model predicted that it belongs to conduction disturbance, then we queried the model again. Like, how do you say that? What have you seen in the ECG wave based on which you're saying that it belongs to this? So you can see blue and red highlighters. So we are then zooming it here, and you can see everywhere it is putting red highlighter on the lower portion where it sees slightly slurred S wave. So indeed, the model is seeing that there is some change in this lower portion based on which it is perhaps saying that it belongs to CD. Now let's look at another example. This is also right bundle branch block, but sometimes what happens is that in the V2 lead, we see an additional peak, which we call as a M wave. Now, again, this is a reference style that has been taken. This is how it looks like. And see, this was the data of the patient. And indeed, there is one additional peak which is going on here. If you zoom in this time, you can see that it is putting highlighter everywhere at that. In every beat, it is actually, at least this portion is highlighted, which is this additional wave. So that means indeed model could see, and that can, if we show this result to a cardiologist, or if the model every time when it comes out with the inference, it also puts this highlighter. We call it as post hoc explainability. If the model is explainable and shows that indeed this is the portion where I have seen a change, which is why I am calling it this, then perhaps the clinician or the cardiologist can trust the model and can, so which is what we always say, that whenever you are building an AI model for healthcare domain, those sorts of explainability should be demonstrated. This is another work that we did where we were looking at 30-day mortality prediction of the patients who were admitted after first heart attack. So this was risk prediction in STEMI patients. Now, again, we designed a custom design architecture. Now, first, let me tell you what are the challenges that we generally face when we work with the real data from the hospital. So this data was also sort of a real data that we received from Jimmy Pant Hospital. So we got the data of around 1,700 patients. Now, out of those 1,700 patients, these were the patients who had first heart attack. They were admitted to the hospital immediately after that. And then they were tracked whether they survived beyond 30 days or some met with mortality within 30 days. Now, the idea here is that if we can make a model at the time of hospitalization itself, if it can predict whether the person has higher chances of mortality within 30 days, so that means that you will maybe admit that patient to the ICU, maybe take recommend a therapy or a treatment which is intense so that you can save the patient. Now, if on the other hand, looking at the features or the way it is coming out at that time, if there is a sort of wrong assessment that perhaps the patient can survive and there is no need to admit or do the hospitalization, or with little bit of thing you discharge the patient. Whereas if it could be predicted based on the the entire metadata or the history of the patient, that the patient has higher chances of mortality, then perhaps you would admit that patient and recommend a different therapy or different procedures so that you can save the patient. So that comes with the significance of the AI model. Now again, but there are challenges also. So the challenge was that only few patients, for example, less than 300 patients, couldn't make it through beyond 30 days, but rest of the patients survived. So that means that there is a huge data of the survival class, whereas there is a very small data of mortality class. Now, with the technological advancements in AI field, now you all must have heard of generative AI. So conditional variational autoencoders are one of the generative AI tools. So we custom designed this architecture and we consider our data for the mortality class, and then we generated some synthetic data corresponding to the mortality class so that we can have now equal number of samples of both the classes. We separated some of the data upfront even before generating the synthetic data. We separated some data upfront of both the classes, but then with the rest of the data that we wanted to use in the training of a AI ML model, some of the data we used for the generative purpose for the mortality class and then build the model. So now we here used again graph convolutional neural network and advanced technology, but custom designed that architecture also and then build that model. So once the numbers were, for example, precision recall, F1 score, our F1 score was also close to 90%. So then we try to look at the post hoc explainability again, whether the model is working or not. So many a times, because we work with the doctors, so we look at the post hoc explainability and we keep going back and forth with the doctors, whether this analysis, is it making sense or not, as per your medical domain knowledge. Now, if the doctors are not convinced, that they say, no, it looks like some of the features that you're saying are the top ranked features, they are not making sense to us, then we would say, okay, fine, let us again look at different model or again make changes to the model and see whether we can further improve it. So for example, here when we built the model, it was a binary classification, but eventually when we built the model and then we looked at what features it is saying are relevant for the survivor class and for the mortality class. So for example, beyond the zero on the right side, it is the mortality class, whereas towards the left, it is the survival class. So if you look at one of the features, for example, ejection fraction, which is less than 35%, we can see that it is red here. So red means that ejection fraction was less than 35%, was less than that range. And so it is actually set to 1. We can see that when it is small, it is leading to mortality because this side is the mortality. If you see ejection fraction 40 to 45, which is greater than 40%, of course, if it is set to 1, that means it would lead to survival. And hence we can see that when it is 1, which is red, then it leads to survival and it is blue here. But it is actually one of the top ranked features. So when we looked at this chart, the higher the, so these features, this is most important, next important, and so on. And we see what is the color on this side, what is the color on that side, which is leading to telling whether it is towards the mortality. When it is higher value, then it is towards mortality. For example, diabetes mellitus, when it is set to 1, it is a cause of mortality, whereas if it is set to 0, it is not a cause for mortality, right? So we see that higher mortality risk factors are almost these, which matches with the domain knowledge. Indeed, it is so. Whereas better survival indicators look like these, which also matches with what is the domain knowledge that is from the medical. This is another work which we did on the real data collected from, again, hospitals. And this was on looking at changes in ECG signals in post-COVID patients. So again, this time we built an in-house architecture and we just took the ECG sample, and the ECG data from every patient was about 10-second data of 12 channels, which is sort of a standard protocol across the globe. And that was collected and that was passed to a custom design architecture. And then we were doing the prediction whether it is a post-COVID subject or a healthy subject. Now, once we did that, and we did in different ways, using the raw ECG data, extracting heart rate variability features, and then adding that to also the architecture and so on. And finally, we built the model. But again, we started looking at what is the post hoc interpretability or explainability. We saw that, for example, there is a P wave notching that was visible and which was also again highlighted in here and showing that indeed it is so, right? So indeed we can see that. So this was sort of a thing that we wanted to see whether there is change in the pattern in the ECG signal of post-COVID patients. So once we have seen that, is our model also capturing those changes based on which it is saying that it is a post-COVID subject or a healthy subject? So some more interpretable results, we also looked at what is the contribution of each lead and how they are playing an important role. So we found that, for example, ABL lead came out to be the most important lead. Contribution of this was most in identifying the changes. And the next lead, for example, was AVR. When we talked to the cardiologist, they said indeed it is so that we find that these leads are really important. AVL is one of the most important lead to look at. So we have in our lab, we have like now we are building the software. So this is a CVC suite that we are still building. So we have created a complete software where you can add a new user patient. We have integrated it with a database, local database, and then we have integrated our first model explainable, then a 30-day mortality predictor model. Nowadays, we are working on this 50 plus CVD conditions if it can do the prediction. So this graph may not be correct, the decision may not be correct because it's just a display of the signals, but this is how the software looks like. All the classes are on this side. So this model is still under preparation because we have still not got the desired results. So once it makes the prediction, if the cardiologist see that this prediction is not correct, then he or she can also pull the label here or pull this label back here. So that way they can work on this and it can be saved. So another benefit that with digitization is that now you can actually build a database and the longitudinal entry would also happen. So you can also see the trends as they are going. And later on, you can also do the prediction whether the person has chances of some disorder or heart condition or heart attack, because many a times we hear that the person was absolutely healthy, but suddenly met with a heart attack. So maybe the person was having some heart changes. So, and those changes could be visible over a period of time. If the technology improves, then maybe, for example, the way we go for yearly diagnosis or some testing, so maybe EEG or heart conditions can also be tested, and those can also be sort of early predictive tools can be built up, and perhaps those therapies can be given to the people. So this is how we have integrated this into a software, and we are now again building it, making it more and more robust so that we can test it in some of the hospitals. This is another model that is also deployed on my lab page under resources page, and it's a working model which is working on my server and can also be tested. So we have also done explainability analysis using different tools. So for example, this is using another tool like Shapley analysis. So again, we have seen on individual patient also which features in that individual patient are leading to the survival or the mortality, and what is the percentage in there. So for example, it should be the probability is 0.64 and probability is 0.34. So you can see which thing has actually contributed to that probability. Then now I'm going to present some work that we have done in cancer microscopic imaging. So I can take a bit of a stop if there are some questions related to the previous slides.
So, ma'am, yes, ma'am, there are some questions, but I think we can take them towards the end. Nothing specific to cardiac for now. Yes, ma'am.
Okay. So now I am going to present some work on cancer microscopic imaging. This work we have been doing with All India Institute of Medical Sciences, Delhi. And so when we talk about imaging area and when we want to build, for example, AI solutions for imaging, it becomes a bit tricky problem, because what we find is that from time to time when images are collected, we see that there are lots of color variations that happen on the images. So for example, if you look at these images here, you can see C1, C2, C3, C4, they have, and the target stain, they have sort of different color contrast in the images. So what happens is that, for example, from even if, let's say that we have been staining the images, staining our peripheral blood smear with, let's say, H&E stain, we find that the staining chemical, it is a chemical. So from batch to batch, there are slight variations that they leave on the slides, and they give a different color contrast. Similarly, because the chemical is there and it will keep on reacting all the time at different temperatures, so we find that if the same bottle is used after, let's say, 2 months, then also it starts leaving a slightly different color contrast. Then your imaging conditions change, maybe with the camera change, which is fixed over the microscope, ambience lighting change. So there are lots of variations that we see in the images that are eventually captured. So we worked extensively on 2 blood cancers, BALL and multiple myeloma. And for both, we captured images under the microscope at IMS. Now, what we found that, for example, for BALL, we collected data over a period of 2 years, and same thing happened for multiple myeloma. We collected over a period of 2 years. But when we looked at the images, we found that over 2 years, lots of variations happened. In between, one of the microscope also got faulty, so the microscope and the camera would change, and that also gave different sort of color contrast. So the first problem that we handled was of stain color normalization. We tried to understand the problem, why it happens, and then we incorporated mathematical components into that, built an in-house pipeline, and did the stain color normalization. So for example, if you fix that this should be the target color, then these are the images you can see, all C1, C2, C3, C4. Now they look like these target scan images, which is what we achieved with this color normalization. Now, why it was important? Because once we do this color normalization, if we now, so for example, in BLL or multiple myeloma, what we wanted to do was that we collected images from peripheral blood smear as well as bone marrow aspirate. For for bone marrow aspirate images were collected, whereas for BLL we collected peripheral blood smear images. And in both cases, we wanted to do classification of cancer cell versus healthy cell. Now, problem is interesting because morphologically, the two cells, whether it is a cancer cell or a healthy cell, morphologically they appear same under the microscope, which is what the pathologists told us. But why the problem is relevant? They said that when the patient walks into the clinic and the clinician suspect that this is the problem, And they say, okay, fine, the test needs to be done. We can make a slide of the blood sample or bone marrow aspirate, and then we can make a slide, see it under the microscope. So if it is BLL, we'll find lots of blast in this of B cell type in the under the microscope, and looking at the numbers which are huge in comparison to a healthy person, we can immediately figure out whether this person is suffering from BLL or not. Now, same for multiple myeloma. Now, the problem happens somewhere else. So, say the chemotherapy has been administered. Now, the number of cells have died, and now the number of cell population is maybe small or as small as what happens in a healthy patient. Now, if you make a slide and look it under the microscope, because they cannot see the morphological change, whether it is a healthy cell or a cancer cell, and the numbers are now in the healthy ranges of healthy, they just don't know how many cancer cells are left. So this time they cannot study that subject under the slide under the microscope. They need to run flow cytometry test. Now, flow cytometry is a costly test, but patient test, maybe it costs 10,000 rupees or so. So if it is a government hospital, it's a bigger challenge. And even if it is not a government hospital, it's a challenge for a patient who wants to get that test done. So we made the hypothesis that maybe using image processing, we can actually figure out whether it is a healthy cell or a cancer cell. And if we can do that, then it becomes a very cost-effective solution. So that was the whole idea of this. So that means that, so we needed to do, first of all, the tagging of the cells, whether they are corresponds to healthy cell or a disease cell or a cancer cell. So you can understand, if a pathologist cannot say that morphologically they find that the two cells are identical under the microscope, how would you label the data for even training an ML model that this is a healthy cell and this is a cancer cell? So what we did was that patients who were not suffering with BLL or multiple myeloma or any cancer, blood cancer type, if they had come for any reason for testing and their slides were made, we labeled all the cells of their slides as healthy cells, and we labeled the cells of a patient who has not been started on therapy and is having a full-blown cancer, all the cells of that person as cancer cells. So this is how we created the label, by looking at the domain, and then we did the classification of cells. So we needed to do the segmentation and then classification of cells. So that's why we propose some of the models. For example, this is one in-house architecture that we made using deep learning, where we were trying to do the segmentation of nuclei in the BLL images, because there the cytoplasm is very thin, it's largely the nuclei. Whereas when it came to multiple myeloma, the data set became very challenging, because you can see here there are clusters of cells. Now, one cell could be healthy, one cell could be diseased, so we had huge challenges on doing even segmentation. So for example, if you can see here, there are 3 cells and the cytoplasm of all the 3 cells are merging. It is very difficult to figure out where the boundaries are for the cells. So the first challenge was that we needed to segment these cells, and then we needed to classify the cells as healthy cells or the unhealthy cells. So we built our custom, again, in-house architecture for multiple myeloma also, because unlike BALL, multiple myeloma cells, you can see here that they have a bigger cytoplasm as well, whereas in BLL, if you look at the blast, you will largely see only the nucleus. There is very thin cytoplasm that may not help in any feature detection. So we made a custom in-house architecture where we used fully annotated data set, means all the cells in the image was annotated manually with their boundaries so that we could segment them and match the performance. Some were unlabeled images where there was no labeling on any of the cell, and some images had partially annotated cells, means if there were 10 cells in the image, only boundaries of maybe 5 cells were made, but 5 cells were left. But we used different state-of-the-art technologies like self-supervised learning, etc., to train the architecture and then propose the results. So we had run an international imaging challenge also on this data, and we could beat the state-of-the-art results on that leaderboard that international teams had participated who won the challenge. Then in another work, then we moved to, once we had done segmentation, we wanted to do the classification. And while doing the classification, we actually came up with an idea that whatever we did in the stain color normalization, if we can bring that knowledge to our classifier and append a layer at the front end that can actually do the task, little bit of task of that stain deconvolution, then perhaps it can give better results. So indeed it gave us better results, and then we further moved on to improving our results on classification. So this work on classification was done on BALL images. And so the idea was, first of all, we wanted to see whether the bringing of the knowledge of stain, the stain normalization that we did, whether it improves results here or not, which we found. And then because the doctors see it under the, using, for example, they do flow cytometry, which is sort of a spectroscopy-based method. So we thought of how about looking at some spectrum-related technologies, and can we really improve the performance there? So here we looked at, for example, this is the cancer cell, this is the normal cell. We used the discrete cosine transform and looked at the spectrum of the two images, and we found that they look almost the same. Then what we did was that we actually did the stain deconvolution, and then looked at the cancer cell and the healthy cell, and then looked at its frequency domain spectrum. And this time we found that there is a change in the spectrum in the frequency domain. We incorporated this knowledge into the architecture, and then we built another architecture. Again, we had created for BLL a data set of 15,000 cell images, curated cell images data set that we released in the open space, as well as organized a International Medical Imaging Challenge in IEEE ISB 2019. And this model that we built later on in 21, it could actually beat the SOTA results on that particular model. So these were the results where this was the challenge results, where we had a weighted F1 of 91%, whereas when our proposed model actually could beat the result, and it came out to be 94.8%. So it was way higher. Then we also looked at the subject level analysis for cancer class and healthy class, because in healthy subject there are very fewer cells, whereas in cancer subjects there are lots of cells. So we could see that there is a change in the performance also. Accuracy when it comes to, or the error when it comes to cancer class is relatively less as compared to healthy class cells. But overall, our results were really good. So again, because the way we were preparing the state of the, labeling the data or preparing our ground truth, in the sense that we were saying that all cells of healthy subjects are healthy cells, and all cells of cancer patients are cancer cells, but that may not be true, because some of the cells in the cancer patient may be healthy. So we built another architecture where we worked on the problem of, we call this as the label noise. That is, when you prepare the ground truth and annotate the data for training an ML model, then there is a noise which is incorporated, in the sense that some cells which are healthy cells, we are mislabeling them as cancer cells. So we call it as a label noise. So we built another architecture where we handled the label noise in the case of multiple myeloma. So this was the architecture. I'll skip that and I'll move.
Sorry to interrupt, but if you can just wrap up in the next 2 minutes and then maybe we can take the questions.
Perfect. Sure. So this was, then we built another architecture that could do stain normalization, segmentation, classification, etc. So some of the medical imaging challenges which we organized and some data sets that we have made publicly available. So I just want to show this, that we have again made a custom design software. We are still integrating models here. So it can actually, you can load whole slide imaging as well as individual microscopic images. And it will do, for example, classification, segmentation as well as classification, and then put those in a separate tiles here. And the doctor can, for example, see WBC, RBC, and can actually, if you say that show all the cells, then it is showing all the cells and also giving labels, and you can actually swap the labels also if they're not correct. So I would like to stop here. Some of the other works that I wanted to show, but I am happy to stop here because indeed it's a lot of work. But my UG and PG students have done a lot of work. I acknowledge funding support. I acknowledge all my collaborators who have really helped me achieve this because we receive data from the hospitals. Thank you. I'm happy to take the questions now.
Thank you so much, ma'am, for making it very simple. So before we go on to the question answers, for the attendees, there's a post-test form. Kindly complete that, and towards the end, Dr. Manu would be discussing the answers for you so that you are sure of what you've answered and got it. Meanwhile, ma'am, I will take you through the questions and what I've gathered from a sense. I think I'll begin with something which was very basic and was asked is, what do I like? There is so much of data lying, and we as clinicians or doctors may not even know what power that data has. So when we are looking at data for diagnostics and for predictions, how simple is what sort of a simplest data can be used? And second, if you can also touch on the aspect where people are wanting to learn Python and these complex architecture buildings, to make them understand of whether moving in collaboration would be more useful than doing it all by yourself. So I think first aspect of the question is this that I would want you to answer, ma'am.
So data. So the first is that you have loads of data, and what do you want to do, or which data is useful, which is not. So as a person who is trained in signal processing, I would say every data that you have is really useful. So whether it comes to as a metadata that you collect, so for example, when we build this predictor, 30-day mortality predictor, what are the simple features like what is your age, gender, whether someone in the family has it or not, do you smoke or not, etc. And all those metadata, they become helpful. That is why digitization, we say these days, if it is electronic health record system, it is really good because you're recording all the information and those longitudinally, they become relevant. Now, what sort of problems you should be addressing with them? So sometimes we say that I want to address a niche problem that it's not possible to actually do it as of now clinically, or we can diagnose that. So that becomes a difficult problem to solve. So I can give you one example why I was emphasizing on this cancer pathology. When I started working with the pathologists there, so we said that we want to create an image processing based solution because that can be deployed in any path lab. So instead of only the cancer hospitals that can do that test, they said, no, it's not possible. We said, why? They said, no, under the microscope, morphologically, both the cells are same. So it's not possible. You can't do any image processing. You can't build any AI in that. Now, our hypothesis was my microscope is not seeing, eye is not seeing, but maybe because there are some cellular changes that are happening in the cell. So definitely, if I use a very deep image processing algorithm, then it should be able to see that. Over a period of time, it was very hard to convince because I can understand there is a domain problem in the way the doctors think and in the way that we engineers think. So the doctors say that we we are evidential people, right? Based on the evidence, we are going to say whether it is there or not. We don't believe in any hypothesis. Whereas when it comes to engineers like us, we say that we hypothesize and we sort of dream. We say that this is what we want to build. And later on, maybe something is built up. And that's how all the technologies are building up. Now you can see that there are LLM models, for example, ChatGPT or not. Someone might have thought that this is what I want to bring in the open domain, but earlier people would say that nothing of this sort is possible. So there is a need of merger of the two. So when we look at the data from every data, we say that every data is useful. So whatever data you have, first of all, you need to see medically what you can do. Building AI ML solution, we don't say that they would be replacing the doctors or the experts. They should be, the AI technology or ML technology should only be used as an assistive technology. So if CVD prediction model is really good, it can be deployed in the night, it can be deployed in the your ICUs, it can be deployed in the vans, and then perhaps the call to the cardiologist can happen when there is an alarm that indeed it is the right alarm and you can be talking to. I don't know, Ashima, how much I have answered it, but I would say every data is useful. Some problems you can make, some problems you should be discussing across with the engineers, and then together you can be actually coming up with some problem. In general, whenever I am working on medical data, I always ask the medical practitioner that what is your problem statement? I wouldn't like to cook up my problem. I need to have your problem, whether it is a small data, whether it is a noisy data, whether the data has some ground truth mislabeling, whatever it is, if you tell me upfront, I would be able to build a model that can address all those constraints and still build a model where I can show post hoc explainability. Once you're convinced, only then utilize the model, not otherwise.
Now, so you did answer, and from the last point, last few statements that you made was actually bringing me to the second aspect of reliability of models that were asked in the Q&A, where people have asked about the even if there's a model available, like you did show some models available on for people to use. How do I trust a model? Because something as simple as a smartwatch these days is predicting ECG for all we know. And here we are talking of intense architectural build-ups to predict a similar thing. So as a medical professional, how do I gauge or how do I rely on a model that people develop? So is there any shortcut to it? Yes, ma'am.
Yeah. So that's why I showed in all our work, in every paper that we do, we bring that post hoc explainability. And I also said during the talk that, for example, any model, so cancer survival model we made for AIMS, and we actually made maybe more than 30 versions of that. Only until in the end when they said that now every rule that we see in this model goes with our domain knowledge, only then we stopped and we said, okay, fine, we have built the model, which is actually correct model. So this is what I generally say even to my students or when we are building the model. So when you are building an ML model, then you talk about precision, recall, accuracy, and all those metrics. Now, I can build hundreds of models and then look at all the precision, accuracy, and all those things. So maybe some model has 93% accuracy, another model has 92.5%, another has 93.2. But which model should I say? The numbers looks about similar. Which model is really a good model? A good model is where the post hoc explainability matches with the domain knowledge, in the sense that when you query the model and say, what have you seen in the data? Just show me those features or tell me those features and the relevance of those, or what you have seen in the images based on which you're saying it is this. If that is what even a specialist sees in the data, and that's how the specialist is also saying it belongs to this class, only then you should trust the model. Now, if that happens and your model is giving accuracy which is slightly lower than all other model, still that model is better, because that means that on the future data, it is going to work according to the domain knowledge, and it is a trustworthy model. Because whenever we are building models, our data is small compared to what it can be used for testing on the prospective subjects. Even if I say I have built a model on 50,000 patients, but maybe my hospital is going to see in next 5 years, maybe 2 lakh patients. Now those data I may not have seen. So your data, howsoever large the data you may use for building an AI ML model, it's still going to be less as compared to what could be the prospective subject on whom you would be taking the inference. So the model should be trustworthy. Now, if someone is selling you a model and is not showing you the post hoc explainability, what it is seeing, then there are doubts. For sure, you shouldn't be buying that model. You should be asking, you should show me what your model is seeing based on which it is saying it belongs to this class. So you shouldn't buy that model at all. You shouldn't latch on to that model. You shouldn't utilize that unless you are convinced. Now it's no more a black box. Earlier we used to say MLDL is a black box. Now it is not a black box. You should have your interpretability as according to your domain knowledge.
Right, ma'am. Thank you. I think we have last 5 minutes, and before we would want to answer any more questions. I think I will invite Dr. Manu Shetty for discussing the Q&A that people have answered. So for those of you who have answered the post-test, Manu, over to you.
And also there is some questions about that audience have asked. So we can go with that answer, then I can...
Okay. A few of them were, I think, covered in the way ma'am has just answered the questions. So, ma'am, Anubha ma'am, can you see the Q&A? Which are like, there are some questions which are still open. And if you want to answer them live.
In the chat?
Yes, ma'am, the Q&A, and there's a Q&A option which is showing like 7 open questions for now. If any of these you would want to address, in the interest of time, we have another 5 minutes or so. We may not be able to answer all 7.
Okay, in Q&A there are...
Ma'am, that I can summarize that one, cardio ResNet model. So you told that mortality states are analyzed by generative AI model, which is again a question. So it is a positive symbol for clinical diagnostics. It's a question. How should approach this medical students who will face such model in upcoming future?
So no. So I didn't say that mortality stats are analyzed by generative AI model. What I said was that the mortality class had very small number of samples compared to the survival class. So we used a generative AI model to generate a lot of data for mortality class so that we could do the class balancing while building the model. And for this, we used only a small amount of data from the whole data set that was available. And we trained the model on the synthetic plus real data and then tested on the real data, which was totally untouched. So no stats were generated by generative AI models.
Yeah. So another question by Amit Kumar. The image normalization is a good idea, but it can cause a bias in image processing. Because in pathologies, the slide stain color can also give a many information. Maybe another model can made without altering the colors.
So very good question. So Dr. Amit, what I mentioned was, so for example, you can't make one stain color normalization method that would be applicable to all types of images. Now here, the stain color normalization that we build separately. For example, if it is for BLL image, then it is the color contrast on the staining, the cells which have been stained. Now the neighborhood is not important for us, right? So we say that it is the reference image. So the target should have color contrast of the reference image, how the nucleus is colored, cyto is colored, background is there, and then it is matching. Our methodology was totally non-ML. It was basically image processing method, but it was very mathematical. and we had tested on number of data sets, as well as we had also demonstrated that if we don't do that stain color normalization and just build a DL model, it makes a huge difference in the results when it is actually stain normalized with our method. So of course, no stain normalization method would be successful if it is altering the stain colors of the neighboring regions, which is not matching with the domain knowledge. So I hope I have answered. It's not that simple that you would simply change the color. In the ratio, the way color contrasts are changing, it needs to match with the domain knowledge, and it shouldn't be altered in terms of when it comes to the texture of the tissues which are going to be identified with that information.
Yes, ma'am. Yes, ma'am. Thank you so much. So over to you, Dr. Manu, for discussing the post-test. We have 2 minutes maybe.
Yeah, okay. I'm not able to.
Ma'am, can you just stop sharing? Oh, thank you, ma'am. So meanwhile, as Dr. Manu is sharing his screen, for all those interested attendees who have joined in, we are happy to announce the MedTech conference which will be happening at MAMC from 5th to 7th December 2025. So for all of you who are interested and are looking for like how do I begin, what do I learn? So please keep checking for our announcements and do join us at MAMC. So I think
can I begin with the post-test questions? Yes. Yeah. So first question is ML, and also Anubhav, correct me if it is wrong. So that and also you can add on to that question. ML model based diagnostic, what metrics commonly used to evaluate the model accuracy? There is various models will be taken, various metrics will be taken, but answer is sensitivity and specificity at present. In addition to that, F1 score, area under the curve, everything is also important. And what is overfitting in the diagnostic prediction models? Overfitting is like second option when the model memorize the training data and perform poorly on unseen data. Like example, some data is taken, train the model, you will get accuracy. When the new data set is taken, it will not give that accurate that diagnosis. That is second option. Question number 3, why the feature selection important in clinical prediction model? Because sometimes, like example, if it is mortality prediction, there's a huge amount, 150, 160 features are there, like age, sex, feature, that various other factors. So we can't include everyone. So every features we can include, but that selecting that relevant data that is improves the model performance. So that's why that option 1 is a better, and we will get a good accurate model. The question number 4, which of the following an example of ML use in diagnosis? So it is a simple question. AI interpretation of chest X-ray. That is among these options. That is a one option. Option A is correct. What ethical issue is the most relevant in AI-based diagnosis? Like already, ma'am has discussed about ethical issues. So that model transparency and data bias is the most important. So thank you, ma'am. If you want to add any final words.
No, it was wonderful for me to talk, and maybe like I know that people might have got lots of questions. So it is really good to talk to engineers, or if you have a team, talk and figure out what is working, what is not working. Those answers are really relevant. Only then we all can trust and build the technologies for the future. It's a great effort that you are doing. And thank you so much. I am honored to be part of this.
Yes, and also like example, another 2 questions. Those who are interested, that is unanswered. So we can take that question also, I think. Yeah. Like how accurate is artificial data generative AI?
So again, the data needs to be tested out, whether it is good or not. So it should be again shown to the medical practitioner and then figured out whether the data is correct or not. So sometimes in automated fashion, we look at the distribution of the real data and the synthetic data and then figure out if the distribution matches, then it makes sense. But whenever you are generating the data, you really need to be cautious enough. So for example, I just give you one good example. Let's say you're generating data of some patients. And so, for example, once we had collected post-COVID and COVID patients' data, we realized that some of the patients' hemoglobin was missing. So we thought that let's impute the data or fill up the data for hemoglobin which is missing. Now we could have just replaced that with the mean value or something, but then when we talked to the doctor, they said no. Subjects for whom we were sure that their hemoglobin is a normal range, that was not collected. Now this is how you're collecting the data. So that also implies that if you are generating the data, you need to be seeing each and every feature that is part of your data, whether it is going in sync with the class level or not. So you can't be otherwise having abnormal values in your features or abnormal data. So there are a number of ways with which you can test the generated data. And that is why we say data curation is the key when you are building AI ML model. So whether it is synthetic data, you need to curate it. That means you need to get it annotated by multiple experts and then see whether the data is valuable or not. Only then utilize that data. Every data doesn't become a useful data. Some might be crap. If it is crap, you will never be able to build a good model.
Okay, thank you, ma'am. And also that one more question was there. I am not able to see now how that it is adapting in present scenario, whether AI diagnostic model, whether they're adapted now at present in real scenario in hospitals. That was a question was there. Yeah.
So I think now technology is moving fast. As far as West is concerned, maybe in US, etc., the technologies are being used. Some software models are also getting FDA approvals, etc. there. So, for example, ECG models have got FDA approvals, etc. So they are being used. But with the current pace with which the LLM GPT models are building up, now the solutions are coming. People are building solutions where it is basically visual question answering. You just show the model an image and then see what you're seeing in that image. It can also label the region and figure out and say that it is actually this. These are the changes I see in this image, and based on this, I'm saying it is this disorder. So now people are working on. We say them as foundational models, and a lot of research is going on. I think in next 2 to 3 years we'll be seeing huge number of AI ML models being deployed in hospitals and being used, because now the pace of the technology, I would say, is one of the fastest at this time post this GPT era. What is happening? It's just out of the box that is happening now.
Right. Thank you so much, ma'am. I think you've made it pretty lucid and simple for us to understand. So I hope more and more people would get more interested in learning and connecting with you. So please, ma'am has been very gracious of sharing her details, and anybody who would want to reach out to ma'am may contact her even at the LinkedIn profile. So with this, we come to the end of the third session in the MIC series at MAMC, and we hope to connect soon next month with another wonderful speaker. Thank you so much, Anuma ma'am, for having for the session, and I thank my MIC team who worked hard to get this seminar running for you.
Thank you, Dr. Ashma. Thank you, Dr. Manu, and thank you, MIC team, and thank you, participants. Have a wonderful night. Bye-bye.
And yes, ma'am. Happy Diwali, and please fill the feedback form for all those who've joined. Thank you so much. Goodbye.